Hello everyone, welcome back to Deeksha Karnataka YouTube channel, and in the Masterstroke series today I am going to discuss about electromagnetic induction. 3 questions you can expect from this chapter, and today we will discuss all the important concepts from this chapter as well as all the important concepts in detail. So first we will discuss the important list of the important concepts from this chapter, and secondly we are going to discuss all the concepts from this chapter. So if you see this lecture, definitely all of your questions coming from this chapter you can answer, okay? And in our live session Tuesday, we are going to solve questions from this chapter as well as the other chapters that we have completed throughout this week, right? So without any delay I am going to start this chapter, and also I am going to inform you about the change in the timing. So all the 9 AM videos that used to go in the 9 AM, now the time is changed to 1 PM for your convenience, so that you can check after the live session at 11 AM is over. You can come and check the videos at your own convenience, right? So with this note, let me start our lecture. First we are going to see all the important concept, electromagnetic induction and magnetic flux, very important. Then we have Faraday's law and Lenz law, both are very important. We have motional electromotive force, then we have inductance, 2 types of inductance, mutual and self inductance, all including all the formulas from the inductance. Inductance is very important concept from this chapter, and then we will discuss briefly about AC generator as well. Now let's start with the session. First is electromagnetic induction, basic definition. Obviously if we are talking about induction, we should know what is electromagnetic induction. Electric currents can be induced in closed coils when subjected to changing magnetic field. So when magnetic field changed related to a coil or associated with a coil, the coil induces a current. The current passes through the coil. That current is called induced current, because normally if you leave the coil as it is, there will be no current. But if you change the magnetic flux associated, changing magnetic flux is very important. Only adding extra magnetic flux will not work. You have to keep on changing the magnetic flux, then only it can produce current, right? Next is the phenomena in which the electric current is generated by varying magnetic field is called electromagnetic induction. So electromagnetic induction is basically the process through which you are inducing the current, okay? Now if you see, there is a coil through which you are moving a magnet, okay? If you move this magnet through this coil in and out, then the field lines associated with the coil changes, and because of that there is an induced current. But if you stop moving this magnet, even though the magnetic field lines are passing through the coil but it is not changing with time, there will be no current, okay? So current will only flow if the magnetic field lines linked with the coil changes with time, okay? Now magnetic field lines into area is flux, so we will say in terms of flux, if the flux changes, current is induced. If the flux is constant, no current is induced. Based on that, we have seen lot of MCQs come in the questions. Now magnetic flux, now we are going to discuss about the definition of magnetic flux. So if you see, there are field lines, there is a surface area, okay, and some field lines are crossing this magnetic field line through this area. So field lines are passing through this area. Magnetic flux through a plane of area A placed in an uniform magnetic field B can be written as phi B equals to B dot A equals to BA cos theta. Now why we have used this phi B? So we have done the same electric flux as well, right? E dot A. Now instead of in electric flux we only simply used the term phi, okay? Now because this is related to magnetic field and not related to electric field, from now on electric flux we will try to address with phi E, and magnetic flux we will try to address with phi B. B is magnetic field, right? So that is why it is called B dot A, and it is a scalar quantity. As you can see, this is a BA cos theta, right? Now let's move on. Faraday's law of induction. So Faraday says that an EMF is induced in a coil when magnetic flux through the coil changes with time. The magnitude of the induced EMF in a circuit is equal to the time rate of change of magnetic flux through the circuit. This is the Faraday's law. Okay, and it is given by epsilon, that is induced EMF. So if there is an induced current, definitely there will be an induced electromotive force as well, right? Voltage in the other term we say. So if there is a current, definitely there will be a voltage, because voltage is responsible for the flow of current. So Faraday basically gave the link between the changing magnetic field and the EMF, that is the voltage required to produce that current. Okay, EMF is the source of the current, so that is why EMF is important. So this is the EMF term, this is the change in flux term. Now the negative sign, even though I have given this negative sign, remember that the Faraday did not give this negative sign. Faraday only said that this epsilon is basically equals to d phi b by dt, right? But later on it was discovered that this is not 100% correct. You have to add a negative sign to it. Okay, that negative sign comes from the another law. We will see that in a while. Okay, the case of closely wound coil of end turns, n number of turns, capital N number of turns. So this is for one coil, one loop basically, and if there is a coil having n number of turns, then the change of flux associated with each turn is the same. So for one coil it is d phi by dt. Now if you have n number of turns, okay, for each turn it is d phi by dt. So what is the total EMF induced? Total EMF induced is given by n d phi by dt. Again the negative sign we will explain in the next part. So now see one MCQ question from whatever concepts we have learned so far. A magnetic field of flux density 1 Weber per meter square. So Weber per meter square is the unit of flux density. Acts normal to an 80 turn coil of 0.01 meter square area. If this coil is removed from the field in 2.2 seconds, the EMF induced in it is. So first of all, flux density is given, that is phi b divided by area is given. Okay, so that is given as 0.1 Weber, sorry 1.0, not 1, 0.1, 1.0 Weber per meter square. Okay, so what is the flask? So flask will be A into 1 Weber, right? So the unit of flask is Weber. So what is the area? Area given here is 0.01 meter square. So 0.01 into 1 Weber, that is 0.01 Weber. That is the flask linked with the coil. Now this coil is removed from the magnetic field in 0.2 seconds. That means the change in the flask is basically the same. So if you remove from the magnetic field, that means initial flask is this, final flask is 0. So change in flask is basically 0.01 Weber, right, minus 0. So 0 is, we are not going to consider. Now what is the time dt? Time dt is 0.2 seconds, right? So what is the induced EMF? So induced EMF is basically given by an 80 turns is there, right? So 80 turn coil. So we know that induced EMF is given by n d phi b by dt. Negative sign we are not interested in this case. So 80 turns, d phi b is 0.01, time is 0.2 seconds. So it will be, if you cancel it, you will get 8 into 1 by 2, that is 4 volts. Okay, 1 0 will remove here, so it will be 0.1. Now 0.1 into 80 is 8 into 1, right? So just do the simple mathematics, remove the decimals, solve it, you will get 4 volt as the answer. Okay, next let's see, that is the Lenz law. So Lenz law, the polarity of induced EMF is such that it tends to produce a current which is opposes the change in the magnetic flux that produces this. So the negative sign comes from this Lenz law. Okay, so if you move the north pole of the magnet towards the coil, okay, the coil will adjust its current such that this north pole and this the induced, there will be, if there is a coil carrying current, we know there is a magnetic field, right? So that magnetic field is called induced magnetic field. This is the naturally occurring magnetic field. This is the primary source. This is the secondary source. Now the secondary source will be such that this repels the original source, or this tries to stop the original source. That is the main thing. Okay, it will always opposes the change. It always opposes the change. For example, I am trying to teach you, but you are listening to something, or you are doing some Instagram scrolling on your phone. So basically there is you are opposed to the change that is going to happen. Similarly, if you take that north pole away from this coil, what happens is that now a south pole is formed, so that again tries to stop that away moving north pole, so that it can stop it, right? So initially it was north pole trying to repel it. Again when it is moving away, then it is a south pole, it is trying to attract and make it stop. So everything happens to stop or oppose the incoming producing current, right? In this case incoming or outgoing magnet. So whatever reason, whatever cause that is producing this current, it always tries to prohibit that, right? This is always important, and the negative sign comes from this fact, this Lenz law. Okay, and this is a consequence of conservation of energy, right? If you just push the magnet, and if it continues to produce current, that means you apply very small amount of energy, but in return you are getting a huge amount of energy, which is obviously not possible by the conservation of energy. Energy cannot be created or destroyed, so that means the energy of conservation has to be obeyed. So Lenz law basically prohibits any excess production of energy, that is the conservation of energy. Now let's move on. Motional electromotive force, another important concept. So the magnetic flask phi b enclosed by the loop PQRS. So here we have a loop, okay, and this rod is basically lying over this rail. Okay, this rail is basically producing a closed loop, okay, and this rail is moving in this direction, and there is a magnetic field into the page of the paper, right? The magnetic field is represented by this cross, so that means the magnetic field is into the page of the paper. Now if you observe that there is a current is getting induced in this coil as it is moving in this direction. Why so? Because initially the flask linked with this loop is entire area times the magnetic field, that is flask linked is basically B into A, right? B is already there is a magnetic field B which is given here, and magnetic field is not changing in this case, but the rod itself moving, so that the flask linked with this coil changes, right? So the area is L into X. Why L into X? This is a rectangle. Rectangle means length into height, that is, this is X, this is X, this is length, right? So this is the area of the coil. Now if you differentiate it, you will get the EMF, induced EMF. So induced EMF is basically given by epsilon is equal to BLV or BVL, okay. This is called motional EMF because it is in motion, it is producing motional EMF. Now in this case, if you see this end is positive and this end is negative, okay. Sometimes they might ask you what is the polarity of the induced EMF. Okay, you can use your right hand rule, okay, to find what is the direction of current as well as what is the so this is the motion, this is the magnetic field, so current will pass from this direction. This is the magnetic field into the page of the paper. This is the right hand thumb where the where rod is moving, right, and this finger will give you the direction of current. So direction of current means this is the direction of current, right? This is the direction of current means obviously this will be plus, this will be minus. Current flows from positive to negative. From this right hand rule you can even find the direction of induced current as well. So direction of current, sometimes they might ask which end will be positive, which end will be negative, or what will be the direction of current. In case they ask you, you can answer those questions right now, right? Remember right hand rule. Okay, this is also sometimes called Fleming's right hand rule. Fleming's right hand rule is for the direction of current in a closed loop. So and this is BVL or BLV, and negative sign obviously is there to compensate the energy, conservation of energy. So now another MCQ, a metallic rod of length 1 meter held along east-west direction and is allowed to fall down freely. Given the horizontal component of the Earth's magnetic field BH is 3 into 10 to the power of minus 5 Tesla, the induced EMF in the rod at an instant t equals to 2 seconds after it released. Okay, so B is given. Okay, and it was given that length is 1 meter, so length is also given, but what is not given is B is given, length is given, time is given, but what not given is the velocity. So we know that induced EMF is basically BVL. Okay, so what is the problem is about? So the rod is falling downward, the horizontal component BH is given, so they are perpendicular to each other. Rod is falling like this, and after 2 seconds, what is the induced EMF across the length of the rod? Now how to solve that? So first we have to find the velocity after 2 seconds. It's a free fall. So free fall means initial velocity, initial speed is 0, and what is the final speed after 2 seconds? So suppose this is t equals to 2 seconds. Okay, so this is t equals to 2 seconds, and we have to find the velocity at this point. If we can find the velocity at this point, we can find the induced EMF as well. How to find the velocity? We know that v square equals to u square minus or plus, in this case, 2 v equals to u plus at. V equals to u plus at, or in this case gt. Why gt? Because it is falling under the gravity, so the acceleration is gravitational acceleration, so gt. So u is 0 given here, and g is given 10, and time is given 2 seconds. So the final speed is 20 meter per second as it is falling towards the ground. Right, now what is the speed? We have calculated the speed. Now we can find the induced EMF. B is 3 into 10 to the power of minus 5. Okay, V we have calculated 20 meter per second. Okay, and length is given 1 meter. Okay, so this will be 320s are 60 into 10 to the power of minus 5, or 6 into 10 to the power of minus 4 volt. Okay, so answer is 6 into 10 to the power of minus 4 volts. Okay, so this is a easy question, but only thing you have to be careful about how to calculate the velocity. Okay, so identify the formula to solve the problem, then identify what quantity is missing, and how can you find that missing quantity can help you to solve such questions. Now let's talk about inductance. Okay, an electric current can be induced in a coil by flux change produced by another coil in its vicinity, or flux change produced by the same coil. Very, very important. So you can induce current in a second coil by either having another coil. So we know that coil itself has a magnetic field, right? If you take this coil and if you move it across it, or if you just change the current by keep on changing the voltage, again magnetic field lines will vary. Okay, magnetic field lines changes with the current, proportional to the current. So if you keep on changing the current, the magnetic field lines linked with the second coil will keep on changing, and based on that you can say that the magnetic flux associated with the second coil will also change, and that will give rise to an induced current. Sometimes if there is no second coil, okay, if you keep on changing the current in a single coil, the coil itself tries to prohibit the flow of current, change of current inside it, because this is also it is actually acting as a self-induced circuit. Okay, so it is trying to induce the current within itself. So this is called self-inductance, and when there are two coils, this is called mutual inductance. Okay, so the flux through a coil is proportional to the current. That is, we can say that flux is basically proportional to I, and change in flux is proportional to di by dt. Okay, so if you remove this proportionality, you can get two different quantities based on what you are looking at. Okay, first is mutual inductance. If there are two coils involved, then that term is called mutual inductance. Okay, let us consider two long coaxial solenoids S1 and S2, each of length L. Okay, so we have two long coaxial solenoids. To remove some of the ambiguities, we are using two coils, both are coaxial. Okay, so now when a current I2 is set up through S2, so what is happening here is this is the outer one is S2, the inner one is S1. So we are changing the current in the S2 circuit, and all the flux line that is originating in S2, they are also passing through S1 as well. Okay, so when we are changing the current in the S2 circuit, okay, there is a magnetic flux linked with S1 as well. Let us denote it by phi 1. Then we can say that N phi 1 is equal to M12 I2. Okay, here the M12 is the mutual inductance of the solenoid S1 with respect to the solenoid S2. Okay, so what we can say that similarly a current I1 is set up through S1, it is set up a magnetic flux through S2, let us denote it by phi 2. Then from again we can say that M2 is the mutual inductance between 2 and 1 when current is passing through 1. So both of them may have a different mutual inductance, but when you compare them, basically you say both of them have the same value. Okay, so M21 is basically equals to M12. So does not matter through which you are sending the current, as long as a current is passing through one of them, and as long as there is a mutual inductance happening, so they have the same value, and the expression for that is given by mu naught N1 N2 A into L. Basically it gives you A1. So smaller one with whatever is inside the core, that area into L is basically the mutual inductance. Okay, now the mutual inductance of a pair of coils of solenoid etc. depends on their separation as well as their relative orientation. So how they are dependent not given, but you have to remember that it depends on the separation as well as their relative orientation. Suppose I have one coil like this, another coil is like this. Okay, so this relative orientation will also change their mutual inductance, and how close or how far they are, that will also change the relative mutual inductance. So mutual inductance depends on their closeness and their distance and their relative orientation. So everything is dependent. Okay, these formulas are not there, orientation and distance, but you have to remember that the relative mutual inductance also depends on these two quantities as well. Okay, now Faraday's law can be written as epsilon is basically equals to minus di2 by dt or di1 by dt, whoever is primary current. Okay, that is the primary current, whoever is the first current, that is the current that you are changing, is this is the primary source, this is the induced EMF in which circuit? Epsilon 1. Okay, it shows that varying current in a coil can induce an EMF in a neighboring coil. The magnitude of the induced EMF depends upon the rate of change of current and mutual inductance of the two coils. Mutual inductance between two coils, as long as their orientation and their distance is constant, is basically a fixed quantity. Okay, it does not matter which coil is primary, which coil is secondary. The coil which carries the current initially at the beginning, that is called primary current, primary source, and wherever the current is induced, that is called the secondary source. Okay, now it is independent of the fact who is primary, who is secondary. That same principle of mutual inductance is used in transformers. Okay, in the next chapter maybe we will discuss about transformers. There you will see that transformers are basically where we use the concept of mutual inductance. Right, now self inductance, it is also possible that EMF is induced in a single isolated coil due to change of flux through the coil by means of varying the current through the same coil. This is the very important thing. This is the same self inductance that we are going to use in the next chapter, that is alternating current. Okay, and Faraday's law can be written as epsilon is equal to minus L di by dt. So you are applying an external electric source, that is EMF, and there is an internal EMF source which is actually opposing the applied source, right? That is why it is called a back EMF. Why back EMF? It is tries to send current in the opposite direction of the original source. So what is the meaning of that? Suppose I have a coil. Okay, I have a variable current source. Now this is sending the current in this direction. Okay, now as soon as the current started to flow through this coil will send a current in the opposite direction. So there will be an induced EMF. This is an induced EMF, say I in. So this induced EMF will send a current in the opposite direction, opposing the original current. So that is why it is called a back EMF. Okay, the term L is called self inductance. The formula for L is given by mu naught n square AL. N is number of turns per unit length. Very important, number of turns per unit length. It is not the total number of turns. Okay, it is the number of turns per unit length. A is area, L is length of the coil. Now same formula is applicable for a solenoid as well, because solenoid is basically a source of self inductance, right? Solenoid, same formula for self inductance for a solenoid can be used. Okay, be careful with this. Now work needs to be done against the back EMF in establishing the current for current I at the instant in a circuit. The rate of work done is basically given by work done is half Li square, and this work is stored as magnetic potential energy. Thus magnetic potential energy is basically half Li square. So if they ask you what is the magnetic potential energy in a self inductance or in a solenoid, it will be half Li square. Also what is the work done to establish the current? That is again half Li square. Okay, it is not zero. Okay, be careful, it is not zero even for a self-induced circuit. Okay, now let's see one problem. A solenoid of inductance 2 Henry carries a current of 1 ampere. What is the magnetic energy stored in the solenoid? Easy question. So magnetic energy stored in the solenoid is half Li square. That is why I gave you, this is sometimes called magnetic energy stored or work done to establish the current. Both have the same terminology. Okay, self inductance is 2 Henry and current is 1 ampere. So it is basically 1 joules. Okay, so 1 joules is the answer, right? Now next, AC generator. This is the last concept of the chapter. An AC generator converts mechanical energy into electrical energy. This is the only way that we are producing electricity in our older days. Okay, nowadays we have solar powered electricity, but this was one of the only way to produce electricity. No matter what type of source you use hydroelectric power, you use ocean currents, you use wind current, and our old coal energy, or even nuclear power station, everywhere this was the only way to produce electricity, that is AC generator. And majority of our day-to-day use even today is coming from this AC generator, tiny little device. Okay, even though the AC generator producing current in the power station are more complex than whatever we are going to study, but this is the basic fundamental principle to produce current. Okay. Now how it is working, it is basically related to a propeller which is connected to a circuit. Okay, that propeller rotates, or we say the turbine rotates, and the rotating turbine is basically fixed with a magnetic frame where there is a coil. That coil also rotates along with the turbine. Now as the coil rotates in the magnetic field, we know that there is a rate change of flux associated with the coil also changes, and because of that there is an induced current. That induced current is collected and sent to our homes for our consumption. Okay, and AC generator basically producing AC current. Okay, and AC current is having the more efficiency because it can be sent from a long distances, right? It can be stepped up or stepped down easily and can be sent via long distances. That is why AC is more popular compared to DC. The induced EMF of a rotating coil of N turns is given by epsilon is equal to N d phi b by dt, and if you do this, you will get the mathematics. This is the formula for induced EMF. We have ignored the negative sign is cancelled here, right? So NBA omega sine omega t. This is the formula for induced EMF in a AC generator. Very, very important. Sometimes we replace this with epsilon naught, and epsilon naught is the magnitude of the induced current. So this is the magnitude of the induced potential, NBAW. You have to remember that induced EMF magnitude is NBA omega. Right, so on which factor it depends? It depends on the number of turns in the coil, it depends on the already existing magnetic field, and it depends on the area of the coil, and it depends on the how fast it is rotating. So basically what is happening, there is a north pole, there is a south pole that provides a pre-existing magnetic field. Very strong magnets are used. Okay, so very strong magnets are used, so there is a magnetic field, and we have a coil. Okay, we have a coil which is carrying current, which is rotating, linked with some turbine or some mechanism, external mechanism. Okay, it can be wind turbine, it can be hydroelectric turbine, it can be coal power turbine. There are different types of turbines. Whatever it is, this turbine is rotating, and based on that this coil is also rotating. So area into magnetic field is the flux linked with it, and every time it is rotating by an angle 90 degree, the flux becomes zero. So it is changing between maximum flux to zero flux, then zero flux to maximum flux. Again the same thing is repeating, and you are getting an AC current like this. Okay, this is the reason why it is called AC generator. Right, now this is the end of this lecture, and if you have any other questions, you can mention that in the comment below. I will be live on Tuesday. Sunday there will be a lecture on alternating current, so don't miss out on that lecture as well. And I will be back on Sunday's lecture, then Tuesday with live session. See you later.